You ever stop and wonder what's really happening when you post a status update or when a million IoT devices all phone home at the exact same time? Well, there's this unseen engine, this absolute workhorse, powering so many of the world's biggest apps. And its design? It's a masterclass in handling a relentless fire hose of data. Today, we're pulling back the curtain on the log-structured merge tree, or the LSM-Tree. So let's just ask it straight up. What is this invisible engine that makes so much of our digital world even possible? To really get why it's so brilliant, we first have to understand the problem it was built to solve. And that problem was actually created by the runaway success of the engine that came before it. And that brings us right to the heart of the matter, the tyranny of random writes. See, for decades, one particular data structure completely ruled the database world. It was perfectly designed for the hardware of its time. But that hardware, and the world itself, were about to change in a huge way. And that ruler was the B-tree. Yeah, if you've ever worked with a classic relational database like MySQL or PostgreSQL, you've used a B-tree. And look, it was a brilliant solution. It organized data into these neat pages to minimize how many times a slow, spinning hard drive had to physically move its read-write head. For a very long time, it was absolutely the perfect answer. Now, the B-tree's whole strategy was built on something called in-place updates. So to change even one tiny piece of data, the database had to go find the right page on the disk, read that entire page into memory, change the little bit of data it needed to, and then write that entire page back to the exact same spot on the disk. This whole read, modify, write cycle was its bread and butter. But that very design, it became its Achilles heel. At internet scale, every single update became a slow, random disk operation, creating this massive bottleneck. This led to a hidden tax we call write amplification. Not to mention, it caused all sorts of locking headaches on modern multi-core processors. And it was especially bad for the new kid on the block, solid-state drives, which can actually wear out from too many writes. So just how bad was this problem? Get this. To update a tiny 32-byte record, a B-tree might have to rewrite an entire 8-kilobyte page. That is a write amplification of 256 times. The database was literally doing 256 times more physical work than it logically needed to. Now just imagine that, but multiplied by millions of updates every single second. It just wasn't sustainable. And it really all boils down to this. The world that the B-tree was built for, a world of read-heavy applications and spinning platters, was gone. The internet brought a new reality, one that demanded incredibly fast data ingestion above all else. That old trade-off of sacrificing write speed for read speed, it just wasn't going to cut it anymore. So this urgent need for a new way of thinking led to a really radical, kind of counterintuitive idea that basically turned decades of database design completely on its head. And this is what we call the append-only philosophy. This right here, this is the mantra of the LSM-Tree. Instead of going through all that trouble to find data and change it in place, what if you just didn't? What if every change, every update, even every delete, was simply a new piece of data tacked on to the end of a log? This one idea, it changes absolutely everything. And that is the log-structured merge tree in a nutshell. Data on the disk is immutable. It is never modified. An update is really just a new version of that record appended to the end of a log. And by doing this, you transform those horribly slow, costly random writes into the single fastest possible operation for any storage device, is sequential write. Okay, so how does this actually work? Well, when a write comes in, first it gets logged in what's called a write-ahead log, just for safety so you don't lose it. Then it's added to this super fast in-memory table called a MemTable. Once that MemTable gets full, its sorted contents are just flushed to a brand new unchangeable file on disk called an SSTable. And poof, from the user's perspective, that write is done almost instantly. But, of course, there's always a trade-off, right? And here it is. To get that unbelievable write speed, the LSM-Tree basically says, okay, I'm going to make more work for myself later. The data is now scattered across all these different files, and the system needs some really clever ways to manage this organized chaos and find things efficiently when you ask for them. And this brings us to the real background magic that makes this whole system tick. It's what we call a symphony of compaction. This is how the LSM-Tree cleans up after itself and, just as importantly, keeps your read performance from tanking. So you've got this read dilemma, right? A single piece of data could be sitting in memory, or it could be in any one of dozens, maybe hundreds of files on disk. How in the world do you find it quickly? And maybe even harder, how do you prove that a key doesn't exist without having to search absolutely everywhere? All right, your first line of defense is this brilliant little piece of tech called a Bloom filter. It's a super efficient data structure that lives in memory and can tell you with 100% certainty if a key is not in a given file. This alone prevents the database from wasting tons of time on expensive disk reads looking for something that just isn't there. The best way to think about a Bloom filter is like a bouncer at a club with a guest list. If the bouncer looks at the list and says, "Nope, you're not on the list," you are definitely not getting in. But if they say, "Yeah, you might be on the list," well, it's worth going to check, right? It might be a false positive, maybe someone with a similar name is inside, but it will never give you a false negative. This simple trick saves countless useless trips to the disk. So the second part of the solution is compaction itself. Think of it like a background janitor process that's always working. It's constantly merging smaller files into bigger, more organized ones. And it has three main goals. First, reduce how many files a read has to check. Second, get rid of old, outdated data to save space. And third, finally get around to physically removing data that's been marked as deleted. But it turns out compaction isn't a one-size-fits-all kind of deal. Engineers have to make a really critical choice here. A size-tiered strategy, for example, is fantastic for write-heavy workloads because it doesn't rewrite the data as often. But a leveled strategy is much better for read-heavy workloads because it basically guarantees that a piece of data exists in at most one file per level, which makes lookups way faster. It's all about balancing those trade-offs for your specific use case. So how do you delete something in a system where you can only add new data? Simple. You write a tombstone. It's just a special little marker that says, "Hey, this key is deleted." When the database is reading and it sees that tombstone, it just stops searching. The actual data, the old record, is only physically removed from the disk much later when the compaction process finally merges the file with the tombstone and the file with the old data. Okay, let's tie all of this together. Why does understanding all this technical stuff actually matter? Because believe me, this knowledge isn't just theory. It's a practical professional superpower for anyone who builds software. At the end of the day, knowing the deep down difference between a B tree and an LSM tree lets an engineer choose the right tool for the job. It's the key to making those huge architectural calls, like deciding between a traditional relational database and a NoSQL one. Getting this right can prevent incredibly costly mistakes before a single line of code is even written. And these engines are everywhere, powering some of the biggest applications on the planet. You've got Apache Cassandra, which is built from the ground up on the LSM-Tree idea to just absorb massive global scale writes. And then there's RocksDB, which was created at Meta, and it's this super tunable engine that acts as the storage layer for countless other critical systems. These are real-world behemoths built on these exact principles. So this knowledge, it really does give you a kind of superpower. It lets you select the right technology for your app's unique needs. It helps you diagnose those tricky performance problems with real precision, and it empowers you to tune your systems for peak efficiency, to go way beyond the default settings and build something that's truly robust and scalable. And that's what's so cool about this. It's not just a black box anymore, right? You can actually see the gears turning. You understand the trade-offs being made, and you know how it achieves that incredible performance. So now that you can see the engine, the only question left is, what are you going to build with it?